Hello students, very good morning to all of you. So in today's class, I will cover up the remaining question of the bending and shear stresses pertaining to engineering services and GATE exam. So let's start. So up to 41 I have covered in yesterday lectures, and from 42 onwards I will cover today. So this is the questions that came in engineering services 2010. Two beams carrying identical loads, simply spotted. There are two beams. Are having the same depth. So depth is same, but this is my A beam and this one is B. But A has double the width as compared to the beam B. So if its width is B, so it will be 2B. The width of A beam is 2 times of width of B beam, and depth is same. Depth is same. This is small d, and then this. So depth of the two beam is same. This is D, and width is 2 times of ratio of the strength of the beam A to that of the beam B. So ratio of the strength, as the strength depends upon section modulus. So strength of the beam depends upon section modulus, means the ratio of strength of A beam to the strength of B beam means ratio of the section modulus of A divided by section modulus of B. As the strength is directly proportional to section modulus, so section modulus of A upon section modulus of B. Section modulus of A will be what is the formula for section modulus? BD square upon 6. 2B, this D square upon 6. In this case, it will be B D square upon 6. The ratio of this is 2. So it means this is the correct option. This is the correct option. Next question. A steel beam is replaced by a corresponding aluminum beam of the same cross-section area, shape and dimensions, and is subjected to same loading. The maximum bending stress will be unaltered, increases, decreases, vary in proportion to their modulus of elasticity. So one is steel beam and another is aluminium. So both the beam have same cross section, shape and dimensions, and is subjected to same loading. Same loading means bending moment of the two are same, and same cross section area, same shape, same dimension means section modulus of this beam Z of steel and Z of aluminium are same. Means if loading is same and if the loading is same, then section modulus will also be same. So section modulus of this is the section modulus of this, as moment of resistance is equal to F into Z. So Z is, F will be M upon Z. So M of steel is equal to M of steel upon Z of steel, and F of aluminium will be M of aluminium upon Z of aluminium. As the same loading means moment of resistance is same and section modulus is also same, so it will be bending stresses will be same. Fs is equal to F aluminium. So bending stresses will be unaltered, as the moment is same means same loading, moment of resistance is same and section modulus of same. It means bending stresses will be same, as the bending stresses is inversely proportional to section modulus and directly proportional to this. So both are same means it will be unaltered. A simply supported beam of span L carries a concentrated load W at the mid span if the width of the beam is constant throughout the span, and then with permissible bending stresses as sigma, the depth of the beam at the mid span will be how much? So in this case, my width is constant but depth is varying. So depth is varying and width is constant, like this. So depth at the center will be, the depth of the beam at the center will be, this load is acting at the center, so reaction will be W by 2, and depth at the center will be equal to this, as bending stresses is this. So permissible bending stresses means maximum bending stresses, bending moment will be maximum at the center. So this bending stresses is equal to, as the formula is M is equal to Fz. The bending stress is sigma, Z is the section modulus, M is the moment of resistance or bending moment. So at the mid span, bending moment will be W by 2 into L by 2. So M is equal to sigma Z and W will be W by 2 into L by 2, WL by 4, and section modulus will be B, depth is at the center is D, BD square by 6. So it will be, D will be 3 by 2 WL upon sigma B and root. So 3 by 2 WL upon 2 sigma B means this one is the right option. Out of the two beams of the same material and same cross section area, one is circular and the other is square section. Each of these is subjected to bending moment of the same magnitude. So both are subjected to the same bending moment, then both sections would be equally strong, both sections would be equally economical. Square section would be more economical than the circular sections. Square section would be less economical than circular sections. As M is equal to Fz, so M is same, but section modulus of the square section is more. So as the section modulus is directly proportional to strength, a beam having more section modulus will have more moment of resistance. So square section has more section modulus. So section modulus of square section is greater than the section modulus of circular sections. It means it will be more economical than circular section. A rectangular beam of width, this is a rectangular beam, its width is 100 mm, is subjected to a maximum shear force of 60 kilonewton. Shear force is 60 kilonewton. The corresponding maximum shear stress in the section is 4 Newton, Q max. Maximum shear stress is 4 Newton per mm square. The depth of the beam would be how much? As we know, maximum shear stress of a rectangular section is 1.5 times the average shear stress, Q average, and Q average will be shear force divided by cross section area. Cross section area is 100 into D. This 60 is in kilonewton, so I will convert it in Newton by multiplied this, and Q max is given as a 4. So from here I can find the D. So D will come here and 4 will come in place of D. So it will be, if I take this, so 15 into 15 is 225 mm. So this 225 mm is the right option. A rectangular beam of dimension B into D is to be cut from a circular log of wood of diameter D. For the beam to be strongest in bending, the dimension will be, so this beam is B and D. So this is a log of wood. So I have to cut this from this one. Maximum cross section which I can obtain from this will be this one. So if I make this diagram, so it will be like this. So this is the dia of the beam, diagonal of the beam. This is also D, and this is equal to diameter of the log. Let's say this angle is theta. So this will be, as this is half of this d, so d by 2 into cos theta sin theta. This is d by 2 sin theta, and this one will be d by 2 cos theta, and this is also d by 2 cos theta. So its total is d by cos theta by 2 into 2. This is d cos theta, and this will be 2 times of this, means d sin theta. So for a beam to be strongest in bending, for a beam to be strongest in bending, the dimension will be how much? Dimension will be how much? A rectangular beam of dimension b into d is to be cut from a circular log of wood of diameter d. For the beam to be strongest in bending, the dimension will be how much? So section modulus of this beam will be how much? Z. Z is equal to BD square by 6. This is the formula. BD square by 6. This is the formula for section modulus. So section modulus of this cut piece of the log will be, B is in this case is d cos theta. This is B into d. D is d sin theta square upon 6. So this will be d cube into cos theta into sin square theta by 6, means d is cos theta into 1 minus cos square theta upon 6, 1 minus, so this is d cube into cos theta minus cos cube theta upon 6. For the beam to be strongest in bending, its section modulus should be maximum. For the beam to be strongest in bending, this Z section modulus should be maximum. For this dz upon theta, this should be equal to 0, and for this dz upon d theta should be equal to 0, and for this dz upon d theta will be this will go in that say. So this will become cos theta, derivative of cos theta is equal to minus sin theta minus 3 cos square theta into minus sin theta is equal to 0, and this will be, the sin theta will go in that side, so it will be 1 plus 3 cos square theta minus 1 plus cos square theta is equal to 0, means cos square theta is equal to 1 by 3, and cos theta will be 1 upon root 3. This is 1 upon root 3, and sin theta will be, as the sin theta is root of 1 minus cos square theta, so it will be 1 minus square of this is 1 minus 3, so it will be 2 by 3. So sin theta is equal to 2 by 3 root. So this sin theta and cos theta is this one, and the dimension of the beam is d cos theta. So this is d cos theta, means d into cos theta is equal to 1 upon root 3. So it will be d upon root 3, and this is width. So this d upon root 3 is the width, and depth is d by 2. This is d sin theta, and sin theta is equal to 2 by 3 root into d. So width is d upon root 3 and depth is root 2 by 3 d, means this one is the right option. A simply supported rod steel joist of I section has flange width of 250 and overall depth of 600 mm. So flange is 250 mm and overall depth is 600 mm. Its moment of inertia is this one. The steel joist is used as a beam over a simply supported span of 6 meter. It carries a load of 40 kilonewton per meter. And this span is 6 meter, including self weight throughout this span. The maximum stress induced in the beam in Newton per mm square due to bending will be how much? So this is the I section. Its overall depth is 600. So it means its stress will be like this. So it will be 300 maximum stress at the top fiber. So M is equal to this maximum bending moment will be WL square by 8. This is the formula. W 40 into L is 6 square by 8. WL square by 8 is the formula. This is the bending moment M, and moment of inertia is I. My formula is M upon I is equal to F upon Y. F is the bending stress. So F will be M upon I into Y, and the bending moment is this one. So this divided by moment of inertia, and remember this is in kilonewton meter, so I will convert it in Newton per mm by multiply by 10 raised to power 6. This divided by I into Y. Y will be distance from the neutral axis and top fiber. This will be 300. So 10 raised to power 6 plus this 2, this 3 into 4, and this is 10, then 5, 4, this is 9. So 5 into 9 will be 45. 45 Newton per mm square is the right option. A simply supported beam has uniform cross sections. B is 100 and depth is 200 mm. Throughout length, the beam is subjected to a maximum bending moment of 6 into 10 raised to the power 7. The maximum bending moment is this one. So m is equal to 6 into 10 raised to the power 7 Newton mm. The corresponding bending stress will be how much? So m is equal to F into Z. Z is section modulus. Section modulus will be BD square by 6. 100 into 200 square by 6. So F will be 6 into 10 raised to the power 7 divided by this one and multiplied by 6. So So 3 into 3, 9 into 10, 90. 90 Newton per mm square you will get. So this one is the correct option. A steel plate is bent into a circular arc. There is a steel plate that it will be like this and it is bent into a circular arc. The plate section is 120 mm wide and 20 mm thick. So this thickness is 20 mm. Young modulus of elasticity is this one. Then the maximum bending stress induced will be how much? So in this case, the radius of the arc is 10 meter. This r is equal to 10 meter. So maximum bending stress is I to calculate. As we know, m upon I is equal to F upon Y is equal to E upon R. So in this case, this maximum bending stress F has to be calculated. Y is the distance of this plate. This will be plate about this axis, and this distance y will be half of this depth. This is 20 mm, so y will be 10 mm. So F upon 10, y is 10. E is equal to this one, and R is 10 meter. 10 meter means 10 into 1000 in mm. So F will be it is 200. So F will be 200 Newton per mm square. This is 200. A fleeced beam. What is fleeced beam? Fleeced beam is that in which there are two metal is a composite beam. One is say steel and timber, or you can say steel and brass, or brass and aluminum. So when two beams, suppose one beam is sandwiched between two beams, steel plate is sandwiched between two timber beam like this. This is steel and this is timber. So this is fleeced beam. So a fleeced beam composed of two different pieces, each having breadth B and depth D, supports an external load D. This statement implies that the two different materials are rigidly connected. So there will be like this. So this is steel and this is brass. So width is B and this depth is D. Now when you glue 2, then this depth will becomes 2 times of D. Now this is B into 2D, a composite one. So they are subjected to an external load. The statement implies that the two different materials are rigidly connected. Rigidly connected means now they are behaving as a single unit. So they will bend about their common axis, neutral axis. They will not bend independently. So it will behave as a single unit. So what does that mean? The two different materials are rigidly connected. There will be relative movement between the two. No movement. Relative movement will not be there. They will behave as a single unit. For transforming into an equivalent single material section, under strength considerations, the depth is kept constant and width will be varied. Yes. Suppose this is the brass. So what I will do, if I convert this steel into brass, I will multiply this by the modulus ratio. To convert this steel into brass, I will multiply it by the modular ratio. So depth will be constant. Only thing is that width will vary. So this is okay. Which of the above statement are correct? So 1 and 3 are correct. In simple bending, strain in the bent beam varies linearly across the beam depth. Yes. If this is a beam, then my stress and strain will be like this. So this is strain diagram and this is stress diagram. So in simple bending, the strain in the bent beam varies linearly. Yes. If this is like this, it will bend like this. So across the neutral axis, the strain will vary linearly. This is okay. As per Hooke law, within elastic limit, the stress is proportional to strain. This is also okay. But both are not connected to each other. So both are correct, but B is not the correct explanation of A. The option will be B. Option will be this one. Both statements are individually true, but statement not 2 is not the correct explanation of statement A. So B is the option. A simply supported beam AB of EI constant throughout when subjected to pure bending. Pure bending means its bending moment is constant. So in case of pure bending, when subjected to pure terminal couples as shown in the figure, will bend into a arc of a circle. Yes, like this. This is true. The theory of simple bending establishes relationship from among M, F, R, Y, E and I. Yes. On the basis of this pure bending theory, I have developed one equation, the flexure formula F upon Y is equal to E upon R. So this formula is totally based on the concept of pure bending. It means both are correct and this is the correct explanation of 1. So A is the option. A simply supported beam of length 4 meter is subjected to a UDL of 2 kilonewton per meter. What is the maximum shear stress if the cross section is rectangular? So in case of rectangular sections, my bending shear stress will be like this. So it will vary parabolically and it will be maximum at the neutral axis and 0 at the top and bottom fibers. And maximum stress is 1.5 times of average shear stress. So maximum Q max is equal to 1.5 times of Q average. So I have to know the maximum shear stress, that is 1.5 times of Q average. And what is Q average? Q average will be shear force upon cross sectional area, and shear force will be, this total load will be 2 into 4, 8 kilonewton. So reaction at both the spot are 4 kilonewton and 4 kilonewton. So total load is 2 into 4, 8 kilonewton. So half will be there. It means my shear force is this. Shear force will be like this, 4 kilonewton, 4 kilonewton. So maximum shear force is 4 kilonewton. So I will convert it in Newton multiplied by this upon cross section area. Cross section area is 100 into 200. So this will be so this is 1.5 into 2 upon 10. It will be 0.3 Newton per mm square, or you can say 0.3 megapascal, because 1 megapascal is 1 Newton per mm square. A mild steel structural section is an unsymmetrical I section with greater width. So this is an unsymmetrical I section. Unsymmetrical, you can say it is symmetrical about the y axis only, like this, with greater width at the top. So I think this is, so greater width at the top will be, it will be like this. The overall depth of the beam is 300 mm. and the flange stresses at the top and bottom of the beams are like this. So at the top and bottom are, at the top it is 150 and this is 50. It will be, suppose this will be under compression and this will be under tension, normal case. So it will be like this. What is the height of the neutral axis from the bottom? So where the stress changes from compression to tension, this is my neutral axis line. So this height from the bottom I have to know. Suppose this is x, so this will be, total is 300. If this is x, this will be 300 minus x. So now this side x upon 50 is equal to this 300 minus x upon 150. So this will be 3x is equal to 300 minus x. It will be 4x is equal to 300 and x will be 75 mm. So 75 mm is, this one is the correct option. What is the shear stress at the neutral axis in a beam of isosceles triangular section with base of 40 mm? This height is 20 mm and subjected to a shear force of 3 kilonewton. Shear force is 3 kilonewton. So shear stress at the neutral axis is to be calculated. So for this, first we must know in case of neutral axis, in case of triangular sections, my shear stress, suppose this is neutral axis, will not be maximum at the neutral axis. It will be maximum at half of this height. So its neutral axis will be 1 by 3 of this. So it is 20 by 3 mm. And the maximum shear stress will be half of this height. Half of this height is 10 mm. So its diagram will be like this. So at the neutral axis, it is 4 by 3 of the Q average. 4 by 3 of Q average. At the maximum shear stress, this maximum shear stresses will be 3 by 2, means 1.5 times of Q average. And remember, it will occur at the mid height, at the 10 mm. But in this question, I have to know the shear stress at the neutral axis. So at the neutral axis, shear stress will be 4 by 3 of Q average. So 4 by 3 of Q average will be shear force upon cross section area. Shear force is this. Now this becomes in Newton. Shear force upon cross section area will be base into height by 2. So now this becomes 10 Newton per mm square, means 10 megapascal. 1 Newton per mm square is equal to 1 megapascal. So this is 10 megapascal. So this is the correct answer. A beam of scarce cross section is placed in such a way. A beam of scarce section is placed in such a way that its neutral axis coincide with its diagonals. Now, this neutral axis coincide with the diagonal. So these are the diagonals. So if you rotate it, you will get this one. Is subjected to a shear force F. So shear force is F. What is the ratio of the maximum shear stress to the shear stress at the neutral axis? So in this case, maximum shear stress will not occur at the neutral axis, rather it will occur at height of 3/8 of this total height. So this total height, suppose this is D. So maximum shear stress will be, what is the ratio of the maximum shear stress to the shear stress at the neutral axis? Yes. So maximum shear stress will be 3/8 of this height. So 3/8 of this D. 3/8 of this, it will occur at this point. Similarly, at this point, 3/8 of this total D. So you will get the maximum shear stress. And at the neutral axis, it is not maximum, but it is less than the maximum. And the maximum stress in this case will be, Q max will be 1.5 times, means 3/2 times of Q average. And shear stress at the neutral axis is 4/3 times of Q average. So this is 4/3 times of Q average, and maximum shear stress is 3/2 times of Q average. So ratio of the maximum stress to the shear stress at the neutral axis means shear stress at the neutral axis, it will be 4/3 times of Q average. So we will get 3/2 into 3/4. It will be 9/8. Means this one is the right option. The intensity of UDL, which when the intensity of the UDL, which when acts over the entire span of 1 meter cantilever beam 1 meter and rectangular cross section of width 100 mm and depth 200 mm. So this is rectangular cross section, width is 100 and depth is 200, would produce a maximum shear stress of 1.5. So maximum shear stress is 1.5, Q max is 1.5 times Newton per mm square, and this maximum is 1.5 times of Q average, and this 1.5 times of Q average. Q average will be shear force upon cross sectional area. This total load is W into 1. So it means reaction here will be W1. W into 1 means W kilo Newton. So this is the shear force. If I convert it in Newton, I will multiply by this by 1000. So this is the shear force divided by cross section area. Cross section area will be 200 upon 100. Now this W I can find from this. So this 1.5 and 1.5 cancel each other. So this W will be 20 into 1. So we will get 20 kilonewton per meter. Means this one is the right option. Two planks each of 50 mm, 50 mm. This is 50 mm. There are two planks. This total becomes 100. So two planks each of 50 mm, 50 mm section are glued together. So they are glued together to form a section of 50 into 100 mm and is used as a beam. If the shear force at the section is 1000 Newton, then what is the maximum shear stress on the glue? Maximum shear stress as the glue. So maximum shear stress at the glue, this will behave as a single rectangular section, whereas maximum shear stress will be at the half. This will become the neutral axis, and this maximum shear stress will be Q max will be 1.5 times of Q average, and Q average will be shear force divided by cross section area. Cross section area will become this 50 into 100. This will behave as a single unit. So this will be 50 into 100. So it will be 0.3 Newton per mm square, means 0.3 mega Pascal. A thin steel ruler, a thin steel ruler of cross section, its cross section is like this. Width is 2.5 centimeter, and this thickness is 0.0625 centimeter. The ends is bent by couples so that it's bent by couple, and at the ends so that its length equal to 25 centimeter. Now this is bent and this length is 25 centimeter. As a circular arc, subtend and central angle of this angle is 60 degree. Theta is 60 degree. Take E is equal to this one. The maximum shear stress induced in the ruler and the magnitude is how much? In this case, as we know, this is a case of pure bending. So this theta is equal to 60 degree. Theta is 60 degree. If I convert it in radians, so 180 degree is equal to pi radians. So 60 degree will be pi upon 180 into 60. It will be pi by 3 radians. So now I can say this angle is pi by 3 in radians, and this pi by 3 theta is equal to L upon R. L is 25 centimeter and upon R. So this is one equation. Pi by 3 is equal to 25 upon R. So this is equation number 1. Secondly, in this case, E is equal to 2 into 10 raised to the power 6. So this is a case of pure bending, means formula, flexure formula is this one. This is E upon R. So I have to calculate the maximum bending stress. So F will be E into Y upon R. So 1 upon R will be, from this equation, 1 upon R will be pi by 3 into 25 is equal to 1 upon R. So I can put this here. So it will be E into Y into 1 upon R is pi by 3 into 25. 1 upon R is equal to this one, pi upon 3 into 25, and E into Y. E is equal to how much? 2 into 10 raised to the power 6 into pi into Y. Y will be distance from the neutral axis. So this ruler will bend like this. So neutral axis depth will be half of the thickness. So half of this. So Y will be 1 by 2 times of 0.0625 divided by 3 into 25. So E into Y is this one into pi by 3 into 25. So from this equation we can find, you can say this f is equal to 2 into 10 to the power 6 into pi into 1 by 2 into 625 upon, this will become 10 raised to the power 4 divided by 3 into 25. So this will be 25, so this will be 4. So it will be 4 pi into 625 upon 3. So 625 into 4 will be, this will be 2500 into pi by 3. So pi by 3 is, pi is 3.14 by 3. So it will be 1.046, something like this. So this 2500 multiplied this one, so you will get 25 into 7, 17. So 26 something you will get. The option is, so you will get 2600 something. So this will be the answer. The bending stress is in a T beam is maximum at the top fiber, at the centroidal fiber and at the bottom fiber. As we know, in case of T beam, dispersion of area is like that. It is more on the upper side, in the flange side. But its neutral axle will be near to the flange. So its bending stresses will be like this. So maximum stress will be at the bottom, rather at the top. Maximum stress will be at the bottom fiber. So this C is the right option. In an elastic analysis of structures, the neutral axis is the intersection between the plane of bending and the neutral plane. Yes, as we know, this is square section, this is a neutral axis. So it will bend like this. So the neutral axis is the intersection between the plane of the bending and the neutral plane. Yes, it will bend along these planes. So above the top, it will be like this, and at this plane it is 0. Bending stresses will be 0. Neutral axis is the context of plastic analysis of structures, is always the equal area. Yes. In case of plastic analysis, which I will cover in the coming lectures. So in plastic analysis, it will be like this. Stress diagram will be like this. So it will be the plane that divides the section into equal area. The stress diagram will be like this. In elastic analysis, it will be like this. So this is neutral axis in elastic, and in plastic it will be like this. So it will be equal area axis. So both are individually true, but this is not the correct explanation of A. So it means option will be B. So both are true, but this is not the correct explanation of 1. in order that the extreme fiber stress in the bending will be in the ratio of 4:3 in the beam shown in the following figure, the width B of the upper flange of the beam section is to be how much? So in this case, suppose this is the neutral axis, so its bending stress diagram will be like this. This is the bending, compression, bending, tension. What he says that the ratio will be, in order that the extreme fiber, oh, I think it's wrong. As in this case, if you see in the figure, dispersion area is more on the bottom flange towards the, so neutral axis will be somewhere here. It will be towards the bottom flange. So it will be like this. So bending stresses, extreme fiber stresses are in the ratio of 4:3. So if this is FC, then FC, this is FT. It means ratio of FC upon FT is equal to 4/3. The width of the upper beam is less than 10 centimeter. The beam section to be what? So this is 4/3. This ratio is 4/3. So 4/3 is the ratio. If you see from this figure, let's say this distance from the extreme fiber is x. This distance is x. So this will be, the total will be 15. So it will be 15 minus x. So this FC upon x is equal to FT upon 15 minus x, and FC upon FT is equal to x upon 15 minus x, and this FC upon FT is equal to 4/3. So it means 3x is equal to 60 minus 4x, means 7x is equal to 60. So x is 60/7, means this distance is 60/7 centimeter. 60/7 centimeter is the distance from the top fiber and the neutral axis. So this is now y bar. So now this is 60/7 centimeter, and as we know, y bar is equal to, this y bar is equal to 60/7, and this equal to area of this B into 2.5. Formula, what is the formula of y1? A1 y1 plus A2 y2 plus A3 y3 divided by A1 plus A2 plus A3. This is the formula. So this y bar will be B into this is the area, and distance is 2.5/2. So it will be 1.25 plus area of this will be, this is 10 into 2.5, and distance from the top fiber to its mid section. So it will be 5, half of this 5 plus 10.5 plus area of this will be 10 into this distance of this neutral axis from the top fiber will be, total is 15 minus half of this it will be 13.75. Half of this will be 1.25. So 15 minus 1.5 is 13.75 divided by area of this B into 2.5 plus area of this will be 2.5 into 10 plus area of this will be 10 into 2.5. So from this equation you can find the value of the B, and this will be, from this equation it will come out to be you will get this one. So this will be the answer. A structural steel fiber has an asymmetrical cross sections. The overall depth of the beam is 200 mm. The flange stresses at the top and bottom are this one. At the top it is 120 and at the bottom it is 80 Newton per mm square. So this is the neutral axis, and overall depth what he says is 200. The depth of the neutral axis from the top of the fiber, suppose this is x, distance of the neutral axis from the top fiber is x. So this will become 200 minus x. So this I have to know. So it means 120 upon x is equal to 80 upon this one. So it will be 600 minus 3x is equal to 2x. So 600 is equal to 5x. X will be 120. So this height is 120 mm. So depth of the neutral axis from the top fiber, top of the beam, this is 120 mm. So this is the correct answer. A rectangular beam of depth d is under bending load has been gradually increased when the top fiber has obtained 5 times the strain at the first yield. So there is a rectangular beam. This is d, or depth is d. So this is b. Load has been increased when the top fiber has obtained 5 times the strain at the first yield. First yield means this top fiber. So I have to find the what depth of the beam will still respond to by the elastic conditions. So as you increase the load, suppose my stress diagram will be like this. So there is a depth x. So this will be d by 2. Let's say this distance is x when the first yield occurs. So this is Fy, means Fy is the yield stress. So when stress at the top fiber, this becomes 5 times of this Fy. What will be the depth of the beam that will still respond by the elastic conditions? So this much depth, so this will be d into this. So this is the portion that will be still under the elastic conditions, this much depth. It means I have to find the x first. So this will be phi Fy upon this this side upon this. So it will be phi Fy upon Fy is equal to, this is d by 2 upon x. It means d upon 2x is equal to 5. So x will be d upon 10. So this is d upon 10, and this depth is 2 times of this one. 2 times of this will be d upon 10 into 2. So it will be d upon 5. D upon 5 is 0.20 d. So this is the correct answer. Now these are the gate questions. For a given shear force across a symmetrical I sections, the intensity of shear stress is maximum at the extreme fiber, at the centroid of the section, at the junction of the flange and the web, at the junction of the flange and the web. So what is the correct options? Obviously, in this case, stress diagram, shear stress diagram will be like this. And this will be maximum at the neutral axis. Neutral axis is at the centroid point. So this is the right option. A homogeneous simply supported beam of width B and depth D and span L is subjected to a concentrated load of magnitude P that can be placed anywhere in the span of the beam. Maximum flexure stresses will be developed when the bending moment will be maximum, and that will be maximum when the load is placed at the center, and that maximum bending moment will be, this is P, so it will be P by 2, and this is PL by 4. So maximum bending moment is PL by 4. So flexure stress is F is equal to M upon Z. M is equal to PL by 4 divided by Z. Z will be BD square by 6, section modulus. So it will be PL by 4 into 6 upon BD square. So it will be 3 by 2 PL upon BD square. 3 by 2 PL upon BD square. This is the correct option. This came in 2006 GATE. A beam with a cross section given below is subjected to a positive bending moment causing compression at the top, and bending moment is 16 kilonewton meter. So M bending moment is equal to 16 kilonewton meter means 16 into 10 raised to the power 6 Newton mm. This is m. So it is causing compression at the, so neutral axis will be the half of this. So it will be like this. This is compression and this is tensile. The tensile force acting on the hedged area. So this hedged area tensile force will be equal to, first I have to find stress at this is the neutral axis, it is 0. So I have to find the stress at this level, and tensile stress at this level I can find from the flexure formula. M upon I is equal to F upon Y. F upon Y. So M is equal to this one. I is the moment of inertia about the neutral axis. This is 150 by 6. This is section. Oh, yes. So this is basically Z. I upon Y. This F will be M upon I into Y. So this will be BD square by 6. You will get bending stress. So M upon I is equal to F upon Y. M is equal to this one. So moment of inertia will be BD cube upon 12. BD cube upon 12. So this is M upon I. F and Y is this one. This is the distance from the neutral axis, and this Y is, in this case, is 25. I have to know the stress at this level. So Y is equal to 25. So I will multiply this by Y. So this you can say 150 into 150 into 150. So 2, 3, 4, 5. So this will be 10, and so you can, this is 3 into 4, 5 and 5. This you can say 2 and 3. So this will be 16. This upon I is equal to BD cube upon 12 into Y is it 25. So this is F, and you can say So this will be 16 into 2 into 4. So it will be 128 upon 9. You can say 128 upon 9 Newton per mm square. So this stress is 128 upon 9 Newton per mm square. So tensile force on this will be the area of this stress diagram. Area of this will be tensile force on this hedged area will be area of this diagram. This is 128 upon 9 is this one. This into this y is 25 multiplied by 1 by 2. You will get area of this triangle, and this multiplied by the width. This width is 50 mm. So this is 50 mm. I will get the tensile force, and that tensile force will be equal to so this is in Newton. So if I divide it by 1000, you will get in kilonewton. So now so this is 80 upon 9. 80 upon 9 means this is 8.9. You can see, means this one is the right option. If a beam of rectangular cross section is subjected to a vertical shear force is V, then shear force carried by the upper one third. Upper one third means, suppose if this depth is D, so upper one third will be this one. This is D by 3. So there are 3 parts now. This is D by 3, D by 3. So upper one third means this portion. So but shear force will be carried by this portion. And remember, this height from the neutral axis is half of the D. So this is D by 2. It means this distance will be D by 2 minus D by 3. So this will be D by 6. This distance is D by 6 from the neutral axis. This is the neutral axis. I have to calculate the shear force carried by this one third. So as we know, shear stress is equal to shear force, which is V, into area of this portion. This area of this portion will be, this is B, into this distance. So this is B into D by 3. This is the area, and So this I have to calculate. So for this, first let us drive this one. Let this distance is y from the neutral axis. So q, this is b and this is d. So q is equal to va y bar upon yb. This is the formula. So v is the shear force, a is the area of this portion. So this is b. So this will be d by 2 minus y, and its distance from the neutral axis, this distance will be, this is d by 2 and this is y. So it will be 1 by 2 d plus y by 2. So this is 1 by 2 of, this is d by 2 plus y. So d by 2 plus y and average of this divided by moment of inertia. Moment of inertia of this will be I into this b. So this will be 1 by 2 v into d square by 4 minus y square upon ib. So it will be now this q is equal to, q now is v upon 2ib into d square by 4 minus y square. So this is the shear stress at this level. Suppose if I consider a small strip whose thickness is dy, so shear force carried by this strip will be q into b is the width and dy is the depth. So I will multiply this by b into dy. So that will be the shear force carried by this small strip. This will be v upon 2ib into d square by 4 minus y square into b into dy. So this is for this small strip. So this b will cancel. So we will get v upon 2I into d square by 4 minus y square into dy. So this is the shear force that will be carried by this small strip. Now if I integrate it from here to here, then this distance is d by, this is d by 3. So this is d by 1/3. So this is d by 6 to d by 2. If I integrate this from y is equal to d by 6 to d by 2, so that will be shear force carried by the 1/3 you will get. Shear force for 1/3 portion will be this one. So this will be v upon 2I and this will be d square by 4 into y. Y will be d by 2 minus d by 6 minus y cube upon 3, and y cube will be cube of this one minus cube of this one. So There is a d cube you can take outside. So this will be d square by 4, 1 by 4 into this will be 2 by 3 minus this will be 1 by 3 into, if you take this common, it will be 27 minus 1. So 27 minus 1 means 26. And this will be Vd cube upon 2i into 1 by 6 minus this one, and this will be 13 upon 108. So this will be 13 upon 324. And this will be Vd cube upon 12i into 324 is the LCM you will get, and this will be 54 minus this one. Anyway, calculation part people can do. So finally you will get the answer. It will be 7V upon 27. So this will be 7 upon 27. You will get, this will be the, its option is the option. This you will get. I section of a beam is found by gluing wooden planks as shown in figure. These are the wooden planks, and I have formed a I section by gluing like this. Now this becomes the I section. If this beam transmit a constant vertical shear force of 3000 Newton, the glue at any of the 4 joints will be subjected to shear force in kilonewton per meter length of this. So any of the glues, if I consider this, then shear stress at this level will be SAY bar upon IB. This is the formula. Shear force is 3000 Newton. Area of this portion, this is 75 into 50 into its distance from this centroid to this distance. This is 100 plus 25 means 125 upon I. I is the moment of inertia, and that moment of inertia will be moment of inertia of the hole, that will be 200 into this is 300 Vd cube upon 12 outside minus this portion, and this will be 75 150 into this distance 200 cube upon 12. So you will get I into B. B will be this one 75. So you will get this is the shear stress at this level. You will get so shear force in kilonewton per meter length. If I convert it in per meter length, means this is in Newton per mm square. So this area, this is 75. I will multiply this by 75 into length. Length is 1000. 1 meter means 1000 mm. So it will give the shear force per meter length, and this is in Newton. So I will multiply this by 1000. So that will be in kilo Newton. You will get this one, and your answer will be this one, 40 kilonewton per meter. The shear stress at the neutral axis of a beam of triangular sections of base 20 mm, base 40 mm, and the side is 40 mm, subjected to a shear force of 3 kilonewton is how much at the neutral axis? So neutral axis is 1 by 3 of this one. Remember, shear stress in this case is not maximum at the neutral axis, rather it is maximum at the height half of this. Half of this is 20 by 2 means 10 mm. So its stress diagram will be like this. It will be maximum here, and maximum will be 3 by 2 of average, and at the neutral axis it is not maximum, rather it is 4 by 3 of Q average. So at the neutral axis the maximum shear stress is 4 by 3 of Q average. So I have to know the shear stress at the neutral axis. So at the neutral axis Q, at the neutral axis will be 4 by 3 of Q average. And what is Q average? Q average will be shear force divided by area of this triangle. Area of this triangle will be 40 into 20 by 2. So this will be 10. So it will be 10 Newton per mm square, means 10 megapascal. The maximum tensile stress at the section XX, at this section, maximum tensile stress at the section X-axis in the figure below is how much? So if you cut this section, at this section, the force is passing like this. It means if you cut this, it will be like this. So you can say this force is P. So same reaction will be here. So it will be, you can say like this. So at the center of this will be this. I can assume my force is like P into this distance. So P into this will create a moment. So this will be like this. If I applied this P and this moment P into D, this is half of this, half of this is D by 2, or half of this will be D by 4. So this is P into D by 4, this is the moment. So total tensile stress at this point will be 1 because of this P, this will be P upon area of this will be, the width is B and area is, this is D by 2. D by 2 means, so this is due to drag tensile force plus due to this moment. This will be M upon Z. Formula is M upon Z, bending tensile. So M is P d by 4 is the moment divided by Z. Z is the section modulus. Section modulus will be how much? This will be BD square by 6. Section modulus of this will be, width is B, and this is like this, and this depth is D by 2. So V into square of D by 2, 6. So you will get, this is 2P upon BD, plus this will be PD by 4 into 6, 6 M upon Z. So BD square upon 6. This is B D square. This will be 4 and it will come here. 6 into 4. So this will be this D and D. So it will be 2 P upon BD plus 6 P upon BD. It will be 8 P upon BD. Means this one is the correct option. Consider a simply supported carrying a UDL having a neutral axis as shown, 4 points P and Q. There is a 2 point, one point is at the neutral axis, another is at the bottom fiber. The state of stress is best represented by which of the following pairs? Which of the following pairs? If you see, this is at P is at the neutral axis, so its stress diagram will be like this. It means at this point P, which is on the neutral axis, my bending stress is 0. So it is neither tensile nor compressive. But shear stress is maximum at the center, maximum at the neutral axis. So at this P point, only shear stress is acting. Only shear stress is acting, while tensile and compressive forces will not be there. This is lying on the neutral axis, means at this point where neither compression nor tensions. So that stresses are 0. Only shear stresses are there. Shear stresses, so it is a case of pure shear, as shear stress cannot act in a single, it will be in complementary shear stress like this. So this is the state of stress at P. So no direct stresses, only shear stresses. It means out of this A and C, both are there. So for Q I have to C. So I have to choose either from A or C. Now if you see bottom at the bottom fiber, it will bend like this. So at the bottom fiber, at this Q, my shear stress is 0. Q is 0 at the bottom fiber, while tensile forces are there. So there is a tension. Tensile stresses are there at the bottom. It is not compressive. So at this Q, only tensile stress will act, direct tensile stress, and shear stress will be 0. No shear stress, only tensile stresses. So it means in this case, if you see, is a tensile stress, no shear stress. So this is the correct option. In this case, you see it is compressive. So it is not right. It is tensile. So this one is the right option. The plane section remain plane assumption bending theory implies strain profile is linear, stress profile is linear, both profile are linear, shear deformation is neglected. So my pure plane section remain plane is based on the bending theory. So strain variation is linear. So this is based on strain relations. This is a linear variation of strain. Strain profile is linear. This is my strain, and stress diagram is also linear. This one is the right option. A symmetrical I section width of each planes is 50 mm. Thickness of so width of each plane is 50 mm. This is also 50 mm. And thickness of the web is 10 mm. Of steel is subjected to a shear force of 100 kilonewton. Find the magnitude of the shear stress in the web at the junction with the top planes. Its stress diagram will be like this. It will vary like this, and suddenly in the web it will increase like this, same, and then again increase. So this is the shear stress distributions. So at this junction, my stress will suddenly jump by width of this and width of this. So it will be 50 upon 10 for 5 times. If this is Q, so this will be 5 times of Q. So this stress I have to know. For this, my formula is Q is equal to SAY bar upon IB. This is the formula. First, I will find the stress at this level. So this is 50. As this is symmetrical, so this will be 10. This will also be 50. This is 50 mm. 50 into 10. Now stress at this level will be, this will be now Q S is equal to 100 kilonewton. 100 means this much Newton. Area of this portion will be 50 into 10 into its distance. This distance from the centroid to this one. This will be 50, and this is half of this. Half of this is 5. So it will be 55 upon moment of inertia of this one. Moment of inertia of this figure will be how much? This is symmetrical. So outside moment of inertia will be, this is 50, and this overall height is 50, 100 into 10, 10, 120. So this is 120 is the overall depth. So this 50 into 120 cube upon 12. This is the outside moment of inertia. I will subtract. So this will be, this is 50 minus 10 is 40. So this one plus this is 40 into this 100 cube upon 12. I will get the net moment of inertia, this I into B. B will be this one, and this is 50. I will get the shear stress at this level. This Q I will get. Once I get this, I will multiply this Q by ratio of the flange width to the web width. This will be 50 upon this web width thickness is 10. I will multiply this by 5. So I will get the answer, and the shear stress at the junction will be, you will get 71.12 Newton per mm square. You will get 71.12. You will get the first moment of area. First moment of area about the axis of bending for a beam cross section is what? Moment of inertia, section modulus, shear factor, polar moment of inertia. So this is neutral axis. So first moment of inertia, as we know, moment of inertia is second moment of area. This is second moment of area. First moment of area will be I upon y. I is second moment of area. Second moment of area. This when I divide this by y, I will get the first moment of area, and this first moment of area will be nothing but the section modulus. A simply supported reinforced concrete beam of length 10 meter sag while undergoing shrinkage. Assuming a uniform curvature of this much, what is curvature? 1 upon r is the curvature. This is given as 0.004. Along the span, the maximum deflection in mm of the beam, this is the maximum deflection, delta. And remember, this delta will be L square upon 8r. So if you calculate from this is L. So this will be L by 2, L by 2, this is R, and this will be R minus delta. Now in this triangle, if you see, this R square will be this L square, this square plus R minus delta whole square. R minus delta whole square means R square plus delta square minus 2 delta R. So this delta is very small, so square of this we can neglect. So we will get L square upon 4 is equal to 2 delta R. So delta will be L square upon 8R. So this is the formula, delta is equal to L square upon 8R. So L is how much? This is 10 meter is the length, 10 square upon 8, and this is R. So this is basically L square upon 8 into 1 upon R. 1 upon R is the curvature, and this 1 upon R is this one. So I will multiply this by 4. So this will be 10 into 10 into 4 upon 8 into, this is 1000. So this is 1 upon 20. 1 upon 20 is how much? 0.05. So 0.05 meter you will get. A 450 mm long concrete prism. This is a concrete beam. Length is 450 mm. Is subjected to a concentrated vertical load of 11.25 kilonewton, 11.25 kilonewton at Q and R. Symmetrically placed 150 mm from this, 150 mm from this side. Cross section of the prism is 150 mm width and 150 mm depth. Considering the linear stress distribution, across the cross section, the modulus of repurchase represented in meg MPa is how much? Modulus of repurchase means bending tensile stress. So this is the FT. This is FC. So modulus of repurchase will be equal to this one. It means I have to find this one. So if you see, so reaction will be same 1.25. So its bending moment will be like this. And this will be 11.25 into this length. And that will be maximum here. So maximum bending moment will be 11.25 is the load in kilonewton, means this much Newton. Multiplied by this length, I will get M. Divided by the section modulus. So we will get the same stress at the top and bottom fiber. This divided by Z. Z is the section modulus. Section modulus will be this B D square by 6. So this way you will get the maximum bending stresses, same will be in the top and bottom fiber. So this is FT, you can say. Now so this is 2 into 2, 4. And if you see, this will be 0.75. So 4 into 0.75 into 4, this will be equal to 3. So this will be 3 megapascal. The answer you will get so this is the end of the lecture. So I hope you enjoyed the lecture. So I hope you enjoyed the lectures. Thank you very much and have a good day.